On an average day, about 50,000 flights move through the National Airspace System. Close to 2 million people depend on that system to keep aircraft separated, sequenced, and moving. From a passenger seat, the infrastructure is almost invisible. A runway appears, the aircraft climbs. Hours later, another runway appears. But between those two moments, the flight passes through a national chain of people, facilities, sensors, radios, software, and decisions. The Federal Aviation Administration says that chain includes more than 400 airport towers, hundreds of radar and communications facilities, thousands of sites, and more than 71,000 pieces of equipment. In fiscal year 2024, the FAA reported 16.1 million flights operating under instrument flight rules and another 14.5 million under visual flight rules. This is not one machine. It is an interdependent system operating across a continent. It has to absorb weather, traffic peaks, runway constraints, equipment maintenance, and the ordinary variation of thousands of daily flights. And it has to do all of that while parts of the infrastructure are being replaced. That is the central engineering problem. Modernization cannot wait for a day when the sky is empty. The old system cannot simply be switched off, rebuilt, and restarted. New surveillance, communication, automation, and staffing capacity have to be introduced while the network continues carrying people every day. To understand why that takes so long, we first have to follow a flight through the system that already exists. At the airport, the most visible part of air traffic control is the tower. Tower controllers manage movement on and around the airport, aircraft on runways, aircraft approaching to land, and aircraft preparing to depart. After takeoff, responsibility moves into the terminal environment. A terminal radar approach control facility, usually called a TRACON, handles aircraft, climbing away from airports and descending toward them. It organizes traffic through the terminal phase between local tower control and the en route system. As the flight climbs into the en route phase, it is handed to an air route traffic control center. Controllers there manage aircraft across large blocks of airspace and coordinate the next handoff as the flight crosses from one center's area into another. Near the destination, the sequence runs in reverse. The en route center hands the aircraft toward terminal control. The TRACON organizes the arrival flow. The tower manages the final approach, landing, and airport movement. The FAA's fiscal year 2024 inventory listed 406 airport towers, 121 combined tower and TRACON facilities, 25 standalone TRACONs, and 25 control centers. Those centers included 21 en route centers and 4 combined control facilities. Above that facility chain is a national traffic management function. The Air Traffic Control System Command Center does not replace local controllers. Instead, it looks across the network and works to keep traffic demand aligned with available capacity. When weather, congestion, or another constraint reduces that capacity, the system has several tools. It can reroute traffic. It can use a ground delay program, hold aircraft through a ground stop, increase spacing through miles in trail, meter aircraft already airborne, or organize flows around constrained airspace. Each measure changes where delay is absorbed. Holding an aircraft on the ground is different from spacing aircraft in the air. Rerouting around weather is different from reducing arrivals into one airport. But all of these decisions depend on information moving through the same national chain. That chain is why air traffic control cannot be reduced to a controller looking at a radar screen. The screen is one interface. Behind it are surveillance, communications, flight plan data, automation, procedures, and other facilities that must agree on what happens next. Modern aircraft can broadcast their own position through Automatic Dependent Surveillance Broadcast, or ADS-B. That capability changed surveillance, but it did not make ground radar unnecessary. The FAA says more than 750 ground-based radar systems remain a surveillance backbone of the National Airspace System. Radar continues to cover airspace where ADS-B is not required. It can detect aircraft that are not transmitting ADS-B or a beacon transponder. It also contributes weather information and gives the system a resilient capability that complements broadcast surveillance. Surveillance, however, is only one layer. A radar return or an ADS-B position has to be associated with flight information, presented to controllers, and carried through the handoffs that move an aircraft across the country. In the continental United States, the primary automation system at all 20 en route centers is ERAM, the En route Automation Modernization System. ERAM processes radar and flight plan data for controllers. The FAA also describes it as a foundation for other capabilities, including system-wide information management, data communications, and ADSB. These names describe different jobs. ADSB helps provide surveillance data. Data communications gives controllers and flight crews a digital path for certain information. System-wide information management supports information exchange. ERAM is the en route automation foundation that processes and presents critical data. The layers overlap because resilience depends on more than one source and more than one path. A new capability can improve the system without eliminating every older component beneath it. That is also why modernization can be deceptive from the outside. Passengers may see a new aircraft display or hear about a satellite-based capability and assume the old network has disappeared. In reality, air traffic control often has to operate old and new technologies together because the national system still needs coverage, backup, compatibility, and continuity. The question is not whether the system contains modern technology. It does. The harder question is how long older systems can remain supportable while their replacements are tested and deployed. In 2023, the FAA conducted an operational risk assessment of 138 air traffic control systems. The result was not a list of 138 failed systems. It was a measure of whether those systems could continue to be supported. According to a December 2024 report from the Government Accountability Office, the FAA classified 51 systems as unsustainable and another 54 as potentially unsustainable. Together, that was 105 systems. GAO reported that 58 of them had critical operational effects on safety and efficiency. The word unsustainable can sound like a warning that a system has already stopped working. In this context, it describes a supportability problem. A system can still be operating while facing outdated functionality, shortages of spare parts, sustainment funding gaps, limited technology refresh funding, or capability shortfalls. That distinction matters. The danger is not always a dramatic failure visible to the public. It can be the growing burden of keeping essential equipment available, compatible, and maintainable year after year. GAO identified 17 systems as especially concerning as of May 2024. The planned modernization work for those systems was not expected to finish for at least 6 years. In some cases, the horizon was at least 10 years. Across 9 selected modernization investments, the planned average time to full deployment was 12 years and 8 months. Some were planned to take between 15 and 19 years. Those timelines reveal the scale of the task. A replacement has to be defined, funded, tested, integrated, deployed across facilities, and transferred into operational use. Controllers and technicians must be trained. Existing traffic still has to be handled safely while the transition occurs. As of May 2024, the FAA had 64 ongoing investments aimed at 90 of the 105 systems classified as unsustainable or potentially unsustainable. But GAO also reported that 4 especially critical systems had no associated ongoing investment. This is the modernization ledger. Systems still doing essential work, programs moving at different speeds, and a replacement cycle measured in years rather than months. Modernization is often announced as a single event. In practice, it is a chain of separate events that should not be confused. An agency can identify a need. A plan can describe a future system. Congress can debate funding. A contract can be awarded. Equipment can enter testing. Individual facilities can receive new hardware. Only later can a nationwide deployment be described as complete. On May 8, 2025, the Department of Transportation published a plan for what it called a brand new air traffic control system. 2 months later, Congress appropriated $12.52 billion for specified air traffic control improvements, with the money available through September 2029. The law included $4.75 billion for telecommunications modernization and systems upgrades and $3 billion for radar replacement. That was enacted funding, not merely a proposal, but it still was not the whole program. In December 2025, the FAA described the $12.5 billion as a down payment and said an additional $20 billion would be needed to complete the entire effort. In January 2026, the FAA announced radar contracts awarded to RTX and Indra. The agency said the contracts would contribute to replacing up to 612 radars by June 2028, with replacements scheduled to begin in the first quarter of 2026 and proceed on a rolling basis. The announcement established contractors, scale, and a schedule. It did not report completed nationwide deployment. The difference is important because a live air traffic system cannot tolerate an ambiguous handoff between old and new. Engineers have to know what data is arriving, where it is going, what happens if a component becomes unavailable, and how controllers will continue working during a transition. Some modernization has already been deployed. The FAA reported nationwide deployment of the Standard Terminal Automation Replacement System in 2021. It has also continued deploying data communications, ADS-B, and surface awareness capabilities through the NextGen program. But modernization does not erase the entire supporting network at once. Ground radar still has defined roles. ERAM remains the en route automation foundation. Communications, surveillance, weather data, flight plans, and facility systems still have to work across a chain with many physical sites. That makes testing and cutover part of the infrastructure story, not an administrative afterthought. A new system has to operate in the real world of weather, traffic peaks, maintenance, and human workload. The long schedule is frustrating, but speed alone is not the goal. The goal is to replace supportability risk without introducing a new operational risk during the replacement. Equipment is only one part of capacity. The other is the time required to develop qualified people. At the end of fiscal year 2025, the FAA employed 13,164 controllers. GAO said that was about 6% fewer than in 2015. Over roughly the same period, the number of flights using the air traffic control system had moved in the other direction. From fiscal year 2015 through fiscal year 2024, total flights increased about 10%, reaching 30.8 million. Those figures do not mean every facility has the same staffing condition. They also do not mean every person counted as a controller has the same certification or operational role. A certified professional controller is different from a trainee still moving through the qualification pipeline. Hiring targets are different from completed hires. Total employment is different from the number of fully certified controllers available at specific facilities. GAO found that the hiring and training process can take 2 to 6 years and involves substantial attrition. That creates a basic timing problem. Even a large recruiting year does not instantly produce a fully qualified workforce. In a plan released in May 2026, the FAA set a full staffing target of 12,563 certified professional controllers. The agency said that as of April 2026, there were approximately 11,000 CPCs at more than 300 facilities and about 4,000 controllers in the training pipeline. About 1,000 of those people had previously been fully certified and were training at new facilities, so the pipeline was not composed entirely of new hires. The same plan set hiring targets of 2,200 controllers in fiscal year 2026, 2,300 in fiscal year 2027, and 2,400 in fiscal year 2028. Those were targets, not completed hires. The distinction is the whole story. A training pipeline is essential, but it is not interchangeable with certified capacity today. A hiring announcement can expand the future workforce, but experience and facility qualification still take time. Air traffic control modernization therefore has two clocks. One measures how long it takes to replace technology. The other measures how long it takes to prepare the people who will operate the system around it. The January 2023 NOTAM outage shows why technical failures have to be described precisely. NOTAM stands for Notice to Air Missions. The system distributes safety information to flight crews and operators. That information can affect flight planning and operational decisions. But NOTAM is not radar. It is not the en route automation that processes radar and flight plan data for controllers. And the 2023 outage should not be described as a failure of the controller separation system. According to the FAA's preliminary review, contractors unintentionally deleted files while synchronizing the primary and backup databases. The agency said it found no evidence of a cyber attack. That finding makes the event less cinematic but more useful as an infrastructure case. A primary system and a backup can still share a failure path when a mistaken action is synchronized between them. Redundancy is not only the presence of two copies, it also depends on how those copies are managed, isolated, verified, and restored. The outage also demonstrates how one information service can affect a much larger operation without being the same thing as every other system around it. Air traffic control is a network of specialized functions. When one function becomes unavailable, the consequences can spread, even though radar, communications, and separation automation remain distinct. That is why labels matter. Calling every disruption a radar failure may sound dramatic, but it hides the engineering lesson. The real lesson is that shared information systems, backup procedures, contractor actions, and recovery plans are part of aviation infrastructure too. The responsible conclusion is bounded. In January 2023, a file deletion event affected the NOTAM system. It did not prove that every FAA database was vulnerable in the same way, and it does not tell us the current condition of NOTAM without a newer dated source. A second case shows why safety failures should not be compressed into one cause. On January 29, 2025, an airliner and a military helicopter collided near Ronald Reagan Washington National Airport. The National Transportation Safety Board completed its investigation in January 2026. Its findings described a layered system problem. The NTSB identified FAA airspace route placement, inadequate review and action, and over-reliance on visual separation among the probable cause findings. It also identified a loss of situation awareness within the tower team under the high workload of combined positions, along with the absence of real-time operational risk assessment. The board listed additional contributing pressures: an unsustainable airport arrival rate, changes in traffic volume and fleet mix, and airline scheduling practices that strain the DCA tower workforce. This is not the same as saying a controller shortage alone caused the collision. It is not the same as blaming one person, one screen, or one policy. The completed investigation described interacting decisions and conditions, airspace design, review processes, separation practices, tower team awareness, workload, traffic, and scheduling. The case belongs in this story because infrastructure includes more than hardware. Routes are designed infrastructure. Procedures are operational infrastructure. Staffing configurations and risk assessment affect how the physical and digital system is used. But the case has a boundary. One collision cannot be used as proof that the entire national airspace system is broadly unsafe. The NTSB findings are specific to this event and the conditions around it. The broader lesson is about layers. Safety depends on multiple defenses working together. When several layers contain unresolved risk at the same place and time, the final outcome cannot be understood by isolating only the last action in the chain. After plans, assessments, and investigations, resilience returns to physical work. It is a technician checking a connector. It is a radio, radar, antenna, cable, power source, and workstation that must be available when needed. It is a facility with an evacuation procedure. It is a trained team that can continue working through maintenance, weather, or a transition to new equipment. The National Airspace System contains thousands of sites and more than 71,000 pieces of equipment. That scale turns maintenance into a continuous operation. Resilience also comes from overlapping capabilities. Ground radar still covers airspace where ADSB is not required, detects aircraft without the expected broadcast or beacon, contributes weather information, and complements ADSB as a backup. But redundancy is not automatic. Two systems can share dependencies. A backup can be difficult to use if trained people are unavailable. A replacement can create risk if the cutover is rushed. A deployable tower can demonstrate the physical possibility of temporary control, but military contingency equipment is not the FAA's normal model for operating the civilian network. The same time problem appears again. GAO found that selected modernization investments were planned across long deployment schedules. It also found that controller hiring and training can take 2 to 6 years. Technology and workforce therefore have to mature together. A new system is not fully useful merely because hardware arrives. People have to understand it, train on it, qualify around it, and trust its behavior under real traffic. This is the less visible side of modernization. The public sees a plan or a contract. The system experiences years of testing, installation, training, maintenance, and parallel operation. Resilience is built during those ordinary years, long before it is tested by an extraordinary day. America's air traffic control problem is not one obsolete computer waiting to fail. It is a national system carrying about 50,000 flights on an average day, while supportability, modernization, and workforce capacity move on different timelines. Some modern capabilities are already deployed. Other systems were classified as unsustainable or potentially unsustainable in a dated FAA assessment. Replacement programs can take years, and controller development can take years as well. So the real challenge is not simply buying newer technology, it is preserving safe, continuous operation while surveillance, communications, automation, facilities, and human expertise are changed in layers. There is no off switch and no empty sky reserved for reconstruction. The system has to keep America in the air while America rebuilds the system beneath it. That work is slow, technical, and mostly invisible, but every ordinary flight depends on it being done carefully.